We're going to continue on. We are on chapter 4, I think. So last time we talked about really the atom and a number of experiments that sort of led to our understanding of the atom. Again, the highlights there. We had the CRT or the cathode ray tube. We have Thomson. We had the oil drop experiment, which was Milligan. Then obviously a major sort of step after some of those experiments was the idea of the sort of plum pudding model of the atom. Again, that was the early model of the atom, where the atom was again thought of as having a very positive charge spread out, embedded kind of negatively charged electrons. At that point, really, the next sort of major one was the gold foil experiment, and that was Rutherford. And again, he shot alpha particles and was sort of surprised at the outcome of that. They expected that most of those positively charged alpha particles would kind of go through the atom sort of with a little bit of deflection. What they found was a lot of them went through with really no deflection, but they did see that they bounced off at some really large angles every so often. So the sort of major outcome was they sort of had to abandon that earlier model of the atom and basically try to explain the results, which was that the atom is mostly empty space. Um, it has a dense positive core, which is the nucleus, and that most of the mass of the atom is the actual nucleus. And later experiments and so forth found out that within the nucleus, we had our protons and our neutrons, with the neutrons again being the most heaviest of all the particles. And both the proton and the neutron, again, is about 1,800 so times heavier than an electron. And that sort of reinforced the idea that the nucleus is actually most of the mass of the atom. And the electrons are out from the nucleus, thank you, at some distance in that empty space, sort of flying around. We then talked about some other sort of properties of atoms, including mass number, which is our number of protons plus our number of neutrons, our atomic number, which is our number of protons. Out of the two, remember, it is only the atomic number that you can find on the periodic table, which once again is the number that is typically above the symbol. And remember, as well as we also talked about, that the atomic number's definition is just the protons. So sometimes people get confused with that because, again, in a neutral atom, the number of protons which are positively charged will equal the number of electrons that are negatively charged in an atom to give it a neutral sort of situation. But again, if you're asked just straight up a question of what is the definition of atomic number, it is only the number of protons. But again, you can kind of get the secondary information from it if it is neutral. Those two numbers are important because if we subtract those two numbers, the protons cancel, and that gives us our number of neutrons. So remember as well that the mass number is not the number on the bottom there. That is the atomic mass. And again, as I mentioned, sometimes confused by people because a lot of times the mass number is a number very close to that number that you see up there. And it's a very common misconception people have that they must have just like rounded or something like that to kind of get to that number. So the way you could kind of remember that for sure is, as we talked about, when you calculate the atomic number, mass number, protons, electrons, or neutrons, they do all need to be positive whole numbers. And that's a really easy way to remember not to use the number on the bottom because pretty much most of those numbers on the bottom are not whole numbers. They're pretty much decimal type numbers. So that's a good way to do that. We also talked about how we can write isotopes, which are the same element, but they do have different numbers of neutrons, which gives them different masses. And the other main thing in terms of our sort of three subatomic particles are protons, electrons, and neutrons. It is the protons that really determine what element you're dealing with. Again, if you look at the periodic table, no two elements have the same atomic number. So it is really the protons that determine the element that you're dealing with. Um, we could write a symbol using the mass number and atomic number. Typically, we take the symbol there, and to the top left, we do go mass number, and to the bottom left there, we go atomic number. So typically, when it is written like that, basically take the top number minus the bottom number, and that will give you the number of neutrons that are present. Another way that we probably don't see too much in this class, but is definitely a way that sometimes they are written. Again, as we talked about, I think the other day as well, it goes something like this, like copper 64. Again, the 64 here is the mass number. You could get the atomic number from the periodic table by looking it up. So the last thing we talked about was sort of the periodic table, I believe. And let me draw my classic box periodic table here. And remember that we used to representative numberings when we use the periodic table. So we got group one here, group two. We kind of skipped the middle, 3, 4, 5, 6, 7, and 8. And again, when we talk about a group, it is going up and down. There's also periods that go left to right across a row on a periodic table. There's 7 periods. In addition, some of these groups have special names that you do need to be aware of. Group 1 is the alkali metals. Group 2 is the alkaline earth metals. Group 7 is the halogens. Group 8 is the noble gases. Those are really stable sort of things. Usually right around boron, you usually will see this sort of staircase coming down. And remember, to the left of the staircase, and also these two guys on the bottom, those are metals, which are usually good conductors of heat and electricity, usually very shiny, and for the most part, solids, most of them, except for not silver, but mercury. If you kind of go upright there of that staircase, you have our nonmetals, and they basically have, again, sort of opposite characteristics: poor conductors of heat, electricity, dull, brittle. On the staircase there, kind of coming down in twos as you kind of come across, those are semi-metals, are metalloids, and those are elements that have properties that sort of fall on both sides along the way. So our metalloids are kind of on that staircase, are semi-metals. In addition, here in sort of this area are, bless you, our transition metals. And as we'll talk about in later chapters as well, one of the key characteristics of transition metals typically is do you have the ability to form more than one type of charge? And that's very common along the way there. And as we also talked about, this is sometimes referred to on the bottom too, lanthanide and actinide series, because technically they go right about there on the periodic table. As if you follow the atomic number, they sort of go in that area. Any questions on any of that stuff we talked about last time? All right, and let us continue on. Obviously, as we talk about some elements and so forth, again, there are certain elements that come basically as twos, as molecules. And remember, the definition of a molecule is really just a basic definition of you basically need two or more atoms to come together. Again, those atoms could be the same. Or they could be different for it to be a molecule. But there are certain elements, as we talked about from the periodic table, that do come as diatomic molecules: oxygen, nitrogen, again, your others there, hydrogen, pretty much all group 7, fluorine, chlorine, bromine, iodine. So again, although they are molecules, they are also elements because they're made up of atoms of only that particular element along the way. And here's a little table from your book of all those kind of elements that are molecules. And it's really important, especially for later chapters as well. Sometimes, for example, when we get into maybe the chapter where we're writing equations or balancing equations, sometimes you are given things in words. And sometimes, you'll be told it's like hydrogen gas or molecular oxygen or molecular hydrogen. And a lot of times people will just write like H or O and can never figure out why nothing will balance correctly because they're not starting with the sort of right form. So you always want to make sure you start with the right formula, especially if it's an elemental form of any of these guys here. You want to make sure you got them as those twos. Otherwise, again, it can cause a little havoc. Pretty much everybody else on the periodic table was referred to as being monoatomic, which means that they basically come as ones. Now, just a little bit about some solid nonmetals, some properties of them. Um, the structures of some solid nonmetal elements are a little bit more varied than metals. You can also have different forms of the same element. And sometimes when you have different forms of the same element, especially nonmetals, they are sometimes referred to as allotropes. And allotropes are really sort of the same element, but sort of the connectivity and how they're kind of put together are a little bit different. Carbon's an example of that. Carbon can be put together in expensive form and make diamonds. Carbon could also put together in maybe not so expensive form and can make graphite like pencil lead. And fullerenes, which are 30 or more sort of carbons put together, sort of visualize like a soccer ball is what those guys kind of look like, is what are known as fullerenes. And here on the left, you can see these are all carbon atoms. On the left is put together in a much different sort of arrangement, and that produces some different properties, obviously, like a diamond. When you kind of put those same carbon atoms together in sort of sheets, you get more of graphite or pencil lead. So you could go get somebody a pencil, go, it's just as good as a diamond, right? It's the same thing. All right, let's talk a little bit more about ions and sort of the nature of it. As we also talked about last time, remember that all elements, pretty much when they are uncombined, they really don't have charges. They typically only gain charges when they sort of hook up. And more specifically, we typically see ions when a metal and a non-metal sort of come together. That is when we form an ionic compound, as we'll talk about in a later chapter. And ions are really anything that has a charge, and as we talked about previously. And again, there's two forms, as we'll get into a little bit more here, and obviously in later chapters. We have cations, which are positively charged, and we have anions, which are negatively charged. So these are basically the two versions of it. And again, this is a result of either gaining or losing electrons, as we talked about the other day. And that is because we cannot change the number of protons, or we will change the element. So when we have a positive ion, as we talked about when we were doing kind of protons, electrons, and neutrons, the result of that is that it has lost some electrons. So if you just think about really every atom has those three things, protons, electrons, and neutrons, except for hydrogen, obviously. But since protons and electrons are the only things that have charges and we can't change our protons, when we do get something that is positively charged, it is a result of it losing electrons. So as we can see here in our example of sodium with no charge, we'll have our 11 protons and our 11 electrons to balance it out, which gives it no charge. When sodium does gain a charge, it is actually group 1, which means it will always make a positive 1 charge. And again, we are locked into our 11 protons because it is sodium. And again, if we change that, it will no longer be sodium. So that means that it has only 10 electrons, which are negative, And if you take 11 positives and 10 negatives, you are left over with a +1 charge, which once again is where the charge comes from. You basically, in this case, have more protons than you do electrons, so you have more positive charge than you do negative charge, and that is how we get there. And again, this is what is referred to as a cation, and cations are typically produced when metals lose electrons. So metals are typically the ones that will lose electrons and form these positively charged cations. Same thing if we take a look at magnesium here. Magnesium, again, with no charge, will have 12 protons, and we'll have a matching number of electrons, which gives you 0. Magnesium, which is group 2, will actually form a +2 charge. And once again, it will still have 12 protons because it's magnesium, but in this case, it will have only 10 electrons. And 12 positive things and 10 negative things leaves you a +2 left over, which once again is where the charge comes from. And again, in comparison to the neutral atom to the one that has a charge, we can see that obviously magnesium with a +2 charge has 2 less electrons. So as we talked about earlier the other day, if you see a positive charge, that should automatically tell you that it has lost electrons, and the number of the actual charge will tell you how many electrons that it lost from the neutral atom. You could also represent sort of this process in an equation. And to represent it sort of in an equation when somebody loses electrons, we could start with something like sodium. And we will then put an arrow to indicate that it has given off an electron. And typically in this case, we will see the electron on the right-hand side of the arrow, which is known as the product side of the arrow. And that's indicating that basically the sodium is sort of given away its electron. So this is sort of a little equation that will represent sodium losing its electrons. Same thing we can see there at the bottom. If we had magnesium, it will give away not 1, but 2 electrons. And again, the electrons there on the product side. Any questions on that there? Now, when we do have positive ions and certain types of positive ions, really all positive ions, the way that we name them is we simply just use the name of the element or the metal. So if we had something like this, which is obviously Na plus, Na is sodium, this would be known as the sodium ion. If we had the Mg2 plus, that is magnesium, this would be the magnesium ion. So positive ions are not too hard to sort of name. If it is a positive ion, it's going to be metal. And if you want to name the ion itself, we basically just use the whole name of it. There are a few other rules that we'll talk about when we get to the naming chapter, especially with metals in the transition metal region. We do actually have to do an additional thing to the name. But the basis of all metal names when they are ions is the actual name of the element. But as we will see when we get to sort of the naming chapter in a few chapters or a couple chapters, for transition metals, they can make multiple types of charges. We also include usually a Roman numeral in their names as well. So for example, if you had Fe2 plus, that is iron. And we do use actually a Roman numeral in this case for the charge ion. And again, we'll talk about the rules when we get to the naming chapters when you do that. But you can still see the basic part of the name is still basically just the element name for metals. Any questions on that there? Now, anions, as we talked about, are again basically the opposite thing sort of happening. When we have an anion, this is typically something that has gained electrons. And again, if we take a look at chlorine as our example, chlorine in a neutral situation has 17 protons, would also have 17 electrons. Again, 17 positives and 17 negatives are going to cancel everybody out to 0. Chlorine will form a -1 charge because it's group 7 on the periodic table. Still got to have those 17 protons, otherwise, again, it would not be chlorine. But in this case, it will actually have 18 electrons. 17 positives, 18 negatives will give us a -1 overall charge. And once again, that is where the charge comes from. Same thing if you did any other sort of guy. If you had your fluorine there, fluorine is number 9 on the periodic table, which means it's got 9 protons and 9 electrons to give you 0. Also group 7, which means it will make a -1 charge, and it will still have 9 protons, and we'll end up with 10 electrons, giving us that -1 charge that occurs here. Now, typically speaking, the result of why they become negatively charged is, as you can see, when you compare the neutral atom to the one that has a charge, then the guy with the charge now has more electrons than it started with. So if you think about it, it will have more negatively charged electrons than protons, and that is why it has a net overall negative charge. And typically it is nonmetals that typically will do this and create anions when they gain electrons. So it's the same idea when you see a negative charge. The negative charge means that it has gained electrons, and the number is how many electrons it gained from its neutral self, if you will. So again, you can see here fluorine with no charge has 9 electrons. Fluoride, which is the negative version of it, has 10. So that's a 1 electron difference, and that is why it has a -1 charge in this case. Now, when we do want to go to name actually negatively charged ions or anions, we do a little bit different than we do with the positive guys. And again, we'll talk in more detail when we get to the naming chapter. But we use the base of the name, and we kind of drop the last part of the name, and we replace the last part of the name with IDE. So instead of this guy here, which is Cl- being chlorine, it becomes the chloride ion. So the IDE here at the end. And instead of F- being fluorine, it becomes the fluoride IDE ion. So when you see in a name IDE at the end of it, it's a pretty good chance that you're dealing with something that is an ion, and a very good chance that it has a negative charge associated with it. And it is not the neutral atom of it. Yeah. So somebody says the bromide ion or bromide, they were not talking about bromine with a neutral charge. They were talking about bromine with a -1 charge in that case. Any questions on that there? So speaking of the periodic table and also ions, let's talk a little bit about the periodic table and the ions that we typically will see on the periodic table. Now, we'll just borrow this here. So everybody in group 1 will always form a fixed +1 charge. So when you go to group 1, everybody there will be a +1 charge. A reminder, as we also talked the other day, remember hydrogen is not a member of group 1. Lithium is the starting group 1. Everybody in group 2 can also be a +2 charge. When we come to group 3, I would say probably 99.9999% of the time you're going to be talking about really aluminum, and that's going to be +3. So it's kind of +1, +2. Again, skip the middle part, +3. Remember, right around here, we got that staircase kind of coming down. We do skip group 4 because there's no real good pattern that sort of happens. When we get to group 5, these guys are nonmetals, and we're talking above the staircase here. So we're talking above the staircase, and we're talking nonmetals. So group 5 is going to be -3. So nitrogen typically makes a -3 charge. Phosphorus there makes a -3 charge. Group 6 is going to be -2. And group 7 is going to be -1. And once again, we are talking about for the minuses above the staircase with our nonmetals, which are typically the ones that make a minus charge. And obviously to the left there, we are talking about obviously metals that make a positive charge. Why is there no good pattern for 4? Well, down here, these are actually metals, and above is nonmetals, so there's no good pattern for 4. Transition metals, as I mentioned before, transition metals actually can make a varied positive charge. So it kind of depends on the situation who you're dealing with. Copper typically can make a +1 or +2 charge. Iron can make a +2 or +3 charge. There are, though, 3, as I might have mentioned earlier as well, there are 3 elements that are transition metals that actually do have fixed charges. And that is like this little backwards L here. You got zinc, you got cadmium, and then hang a left there to silver. So these 3 sort of transition metals, although they are transition metals, they do have basically fixed charges, with zinc and cadmium being +2 and silver being +1. Yeah, so zinc and cadmium +2 and silver being +1. Pretty much everybody else, though, in this region, and also down here where we have like lead and tin and antimony, they actually can make varied sort of positive charges. These are really good to know, especially when we do get to the naming chapter, depending on whether or not the metal can make a fixed positive charge or a varied positive charge is how we name them as well. What we do, either it's really whether or not we put the Roman numeral in there or not. So things with positive fixed charges, we typically don't use Roman numerals. And when things do have a varied charge, we do use the Roman numerals. So that's a really important thing to know. So it's kind of 1, 2, 3, skip on 4, and go backwards 3, 2, 1. Again, positives on the left, negatives on the right in that case. Any questions on that there? And when I talk about fixed charges, I am talking about sodium, for example. You will never find sodium with like a +2, +3, +4 charge. It's always just 100% of the time going to be a +1 charge. So it'll never make anything other than that. And again, that's why we really don't need to use, as we'll talk about in the naming chapter, we don't need to use things like Roman numerals, because when somebody sees the sodium with a charge, they should always know it can only do +1. So there's no guessing game. But that's also why, as we'll talk about, we do need the Roman numerals when we do iron, because it could be iron 2 in certain cases, could be iron 3. So we have to tell people, hey, in this case, it's like number 2. In this case, it has a +3 charge. Any questions? All right, here. We'll talk a little bit about the electrical nature of matter. And when we are dealing with ions, there are certain substances that if you dissolve in water and make a solution will conduct electricity really well. And those things are what are known as electrolytes. And electrolytes, for our purposes, are really substances that when they go for a swim in water, they will basically dissolve and they will basically form a bunch of ions. And it's actually the ions here that is what allows electricity to be conducted. So the presence of ions is really what helps sort of conduct the electricity here. And depending on whether you have a lot of ions or not so many ions, you can actually have different types of electrolytes. So let's talk a little about the different types of electrolytes. There are what are referred to as strong electrolytes. And when we have a strong electrolyte, it will 100% break apart into ions. So when you have a strong electrolyte solution, you pretty much have only ions in that solution. So if you took sodium chloride and you dissolved it in water, you would make a sodium chloride solution that is aqueous, which is basically a water environment. And basically what's going to happen in that sodium chloride solution is you will have sodium ions floating around and you will have chloride ions floating around. You will have 100% ions floating around. You'll have none of the NaCl units still together. There is no NaCl unit like floating around. It's going to completely break apart. And when you look at like your beaker, pretty much all you're going to find are sodium ions floating around and chloride ions basically floating around. So because there is a lot of ions produced in that solution, and by the way, they are floating around with water molecules basically surrounding them, as we may have talked about the other day as well. You have pretty much a good situation that is going to conduct electricity very, very well because there's a lot of ions in that solution. So the classic example, we don't do it at this school, but a lot of times people will take a light bulb that's hooked up with some electrodes, and you can stick the electrodes into a strong electrolyte solution like a sodium chloride solution here, and the light bulb will turn on very bright. Yeah. It will turn on and be very, very bright because there's a lot of electricity being conducted, and light bulb, super bright. Now, in a weak electrolyte solution, which is another type of electrolyte solution, for example, if we take a weak acid like hydrofluoric acid, when it breaks apart, will break apart into H plus and F minus in this case. And this is a weak acid, which is a weak electrolyte. And what will happen in this particular case is, unlike the strong electrolyte, when you have this sort of solution happening, this is mainly what you have in solution. You do have some of these guys formed, but it is not going to completely 100% break apart. So if you were to kind of look at that beaker, you would actually see the HF, well, not you could physically see it, but you would have the HF sort of molecules still together. You will produce a little bit of sort of ions in that solution, but it's mainly going to kind of stay together, not really break apart into ions. The result of that is you will end up with a solution that still has ions in there, but not as many as it would be if it was a strong electrolyte. So because there's still some ions, it will still conduct electricity, but it will not conduct electricity anywhere near as good as a strong electrolyte. So if you did sort of the light bulb example, where you kind of stick the light bulb in with the electrodes, it would turn on, but it would look very dim, like it's almost dying, but it would still kind of power up, but probably maybe not give you a lot of light. But it would still kind of turn on. Again, because there's still presence of some electrolytes, ions in that solution. One of the main ways that you can kind of tell the difference between the two, especially in equation form, is you can see on this one, there's actually 2 arrows versus this one, which is 1. And typically speaking, when you see like a 1 arrow, it's kind of like you could think of it like a one-way street. Everything is just going to the other side. So everything's going to what's known on the right-hand side of the arrow as the product side. In a situation where you have 2 arrows, they're actually pointing in opposite directions, which means this reaction here, when you see sort of this setup, this is a reversible reaction. So this is a reversible reaction, and it has 2 directions. It has going from reactants to products. Reactants are on the left-hand side of the arrow, what you start with. Products are on the right-hand side of the arrow, what you end with. That's what's known as the forward direction. And then what happens in these type of reactions, which is a little different than sort of our one-way street, is at some point when you produce enough products, those products will decide, hey, I want to come back together and go back the other way. And they will actually recombine on the right-hand side and head back in the other direction and form what you started with. And that is what is known as it goes from right to left as the reverse reaction, or the reverse direction. And what happens is eventually the rate with that happens, the forward and the reverse direction will actually equal each other. And that is what's actually known as chemical equilibrium. And if you want to know more about chemical equilibrium, that's pretty much the entire topic of Chem 1B. So when you get to Chem 1B, you talk about every equilibrium maybe you never want to know about, but that is the idea there. You talk pretty much about all these type of reactions that tend to head in opposite directions. I would say in terms of weak electrolytes, mainly weak acids and weak bases are very common weak electrolytes that you come across. So how do you know maybe it's a weak acid or a weak base? Not that we're going to come across a ton of them in this class or anything like that, but as you continue on, and we'll talk about it in a later chapter, but one way to maybe figure out if you're dealing with something that's maybe a weak acid or a weak base, the good way to do it is probably process of elimination. And the way you can do that is if we go back one step, a number of strong electrolytes are actually strong acids and strong bases are strong electrolytes. So when we talk about strong acids, there's actually only like 6 strong acids that you usually come across: hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, and hydriodic acid. So these 6 acids are strong acids, and they would fall under the category of a strong electrolyte. So typical strong electrolytes are usually ionic compounds, are strong electrolytes, and strong acids are strong electrolytes, and also strong bases. Now, what about bases? Well, strong bases can almost be found by looking at things like sodium hydroxide, potassium hydroxide, calcium hydroxide. Pretty much, if you see somebody from group 1 or 2 on the periodic table, and it has hydroxide in it, OH minus, which is hydroxide, it's probably going to be a strong base. So if you look at the periodic table, and we'll talk more about it when we get to actually the acid and base chapter, but just for our purposes here, if you look at the periodic table and you go to where lithium is and you go to sodium, you go to potassium and hang a right-hand turn at potassium, and go to calcium and then go down, strontium and barium. Any of those guys that pretty much has OH with them is most likely going to be a strong base. So that's a good kind of way to recognize it. So just kind of knowing those 2 things, that those guys are going to be strong electrolytes. If you happen to see something that you know is maybe an acid or a base that's not one of those, then you're going to probably be more like a weak electrolyte. Any questions on that there? Now, the last type of electrolyte is what's known as a non-electrolyte. And with a non-electrolyte, it will basically dissolve but not produce ions. And that's really the important part here. When you have a non-electrolyte, it will dissolve, but it's actually not producing any ions. So a very easy example of that is sugar. If you take some sugar and you dissolve it in some water, you get some sugar that's dissolved, right? Now, sugar is basically made up of carbons, hydrogens, and oxygens, and those guys are held together by sharing of electrons. You're not going to produce any ions in this case. It's not going to break apart. Actually, just the whole thing just dissolves basically for a lot of reasons. And one of those reasons is there's a lot of OHs all over sugar and works really well with water. But because there's no ions in this case, so when you have your thing of sugar water, you have no ions, you're not going to conduct electricity. So if you did your light bulb sort of example, it's not going to turn on. And again, that is because of the lack of ions that are present in that solution. If we have just pure water by itself, is pure water a good conductor of electricity? The answer is no, it is not a good conductor of electricity if you have pure water, because water is held together by sharing of electrons, no ions. Now, just to be safe, right, obviously the water that comes out of your pipes is not pure water. There's a lot of ions in it. They actually put ions in it to clean it, and you will electrocute yourself if you decide to blow dry your hair in the shower. Do not do that. Safety note for anybody listening. But again, if you have just pure water, there is no ideally ions in that, and it should not conduct electricity. Dissolve a little bit of salt in that. Now you have like sodium ions and chloride ions. Now you got a solution that's going to dissolve, conduct some electricity. Any questions on any of that there? So here's the sort of experiment that's sometimes done in schools, and to sort of show you, again, we basically have some electrodes hooked up to a light bulb, and on the left, we have just pure water. And again, because there's no ions in pure water, the light bulb will not go on. It's not going to conduct electricity. Like I said before, sprinkle a little bit of salt in there. You now got some positive and negative ions floating around in the solution. Now you're good to go, and it's going to basically conduct electricity really well. This is how ionic compound look like. When we have an ionic compound, it typically consists of two things. It consists of a cation that is positively charged. It also consists of an anion that is negatively charged. And again, it is that opposite attraction which holds them together. And as you can see in this is typically what ionic solids look like. They arrange themselves in a really ordered pattern where they try to maximize the attraction between the positive ion and the negative ion and minimize the negative and negative being near each other and positive being near each other. No matter what you do, they are going to kind of be near each other, but they kind of move around to they minimize it. We also see in this picture, if you look at it, the size of the positive ion is actually smaller than the size of the negative ion. So if we think about what happens when we make a cation versus an anion, when we make a cation, we lose electrons. So if you think about those electrons that are moving around in the cloud, as they lose electrons, right, you lose some of that electron density, the overall size shrinks. As we gain electrons, we're going to add to that electron density, and the size of the anion versus neutron will be larger. Do you have a question? Are you talking about the circles here? Yeah, so it'll be a similar arrangement. Um, the size of the ions in general, if it's positive, will be smaller than its neutral counterpart. The actual size measurement will vary depending on what element you got going on. Yeah. Other questions? Okay. Now, one last thing here in this chapter, and again, we definitely will go into a lot more detail when we get to the actual naming chapter, but in this chapter, since we are talking about ions, when we do put together a formula for an ionic compound, and that is typically always, by the way, 100% of the time, the ionic compound. It is always a metal and a non-metal together. So as you go through, obviously this class and other classes, if you see basically something that's a metal with a non-metal, it should be automatic that you're dealing with an ionic compound. It should also be automatic that this metal ion probably has lost some electrons and is now a positively charged guy. And this guy has gained some electrons and now is a negatively charged guy. And once again, one of the important sort of cornerstones of an ionic compound is they actually do not share electrons. So what holds these guys together is just simply that attraction between the positive and negative charges, and that's what holds them together. There's absolutely no sharing of electrons sort of happening in this situation. So when we write formulas for ionic compounds, this is always the order it should go. It should always go the positive guy first and the negative guy second. And when we put together the formula for an ionic compound, the overall charge, when you do that, when you put the positive guy together and the negative guy together, the overall charge doesn't equal 0. And you need to get it to 0 in the simplest way possible, because ionic compounds come together in the simplest way possible. They come together in what's known as empirical formulas, simple ratios that get everybody to 0. So, for example, if we were going to take a sodium ion and put it together with a chloride ion, when we put this together, that's +1, -1. We just need one of each, and we get the formula of sodium chloride. As you can also see, when you write the formula for sodium chloride, which is an ionic compound, there is no charges included. Yeah, so it is a neutral sort of formula, but it is actually made up of, as you can see, two things that do have charges. So when you see something like NaCl written, it is sodium with a +1 charge. It is Cl with a -1 charge. They are actually ions, but we never include the charges in a chemical formula for an ionic compound. So it's just implied that we're dealing with those ions, and we don't do that. So if we took something like calcium, which is the next example, which is a +2, because it's group number 2, and chloride, which is -1 from group 7, when we put these together, we have a +2 and a -1. And if you add +2 and -1, you do not get 0. So we need to get it to 0 in the simplest way possible. So we actually need not one, but we need two of those guys. And that gives us a -2 overall to balance out the +2 that we got going on with the calcium. And when we write the formula for this, we do have to reflect that. So when I look at calcium, I only have 1, right? And when I look at chloride, I have 2. And remember, the subscript goes to the guy to the left. So when you see CCl2, it is telling you you have one calcium ion that has a +2 charge, and you have two individual chloride ions that each have a -1 charge. A very common mistake that happens, especially when we get to the naming chapter, is people will look at this and they will be asked to write the formula of the anion, and they'll write like Cl2 on the bottom and -1 on top, and that is not correct. So that 2 on the bottom, in this case, because it's an ionic compound, indicates that you have 2 Cl minuses, not that you have something like Cl2 on the bottom, -1 on the top. So that's really important. So same idea here. If we take a look, if we took barium and put it together with oxygen, barium's group 2 has a +2 charge. Oxygen's group 6 on the periodic table has a -2 charge. +2 -2 means we just need one of each here. So BaO, again, that means one barium and one oxygen. As we talked about at the beginning of the chapter, we do not typically write 1 ever, right? So if you don't see a number there, it is 1. We take a look at aluminum, which is group 3 +3. Sulfur or sulfide is group 6, which is -2. When we put them together, we want a common number to get us to 0. The easiest way to do that is just multiply the two numbers together, right? 3 times 2 is 6. So to get my aluminum to 6, I need not 1, but I need 2 of them. That's going to get me a net +6 charge happening. To get my sulfide to 6, I need not 1, not 2, but I need 3 of them. This can give me a -6 overall. Now I have everything I need to write my formula. I could frankly just count what I just did there. I have 2 aluminums, which means I should have an aluminum with a 2 next to it. And I have 1, 2, 3 sulfurs and a 3 next to it. And that will give us our proper formula. Once again, when we look at the formula here of the ionic compound with the metal and non-metal together, no charge. But again, it is made up of cations that have charges and anions that have charges as well. So it's a really important thing. Last one on there is getting kind of cut off there. We got potassium, which is group 1, and we got phosphorus, which is group 5, has a -3. Once again, when we put this together, basically 3 is the number is going to get us there. So I need not one, not two, but I need three of those guys to give me a +3 to balance out my -3 charge that I have going on there. If I just count it, I have 3 potassiums, which means I need to put a 3 next to it. And I have only 1 phosphorus, and that would get us our proper formula in this case. Any questions on that? By the way, to name these, all these metals in each of these cases all come from group 1, group 2, or group 3, which means they all have fixed charges, which means you don't have to use Roman numerals. So, for example, CaCl2 is calcium chloride. BaO is barium oxide, IDE. Al2S3 is aluminum sulfide, IDE. And obviously NaCl is sodium chloride. So again, as we talked about earlier, for the metal, whole name, and the non-metal, IDE at the end of the name for each of those. Any questions on any of that there? All right, that is chapter 4. We're then going to go now to chapter 10, I think. Okay, we're off to chapter 10. So a couple of things about chapter 10, which is, when they wrote the book, they went in order. So they see if you're at chapter 10, you maybe did all the previous chapters, which obviously you haven't done yet. So we're going to talk a little bit here up front just about chemical equations and reactions, just so, again, we understand when we're talking about products, reactants, what's going on, because obviously they assume maybe you did chapter 6 and 7 already, but how you got to 10. So we just talked about it a little bit, but here just to give us sort of a understanding of when we talk about those things, in a chemical reaction, we can basically represent it with a chemical equation. And when we look at an equation, they are typically written like this. They are what are known as reactants on the left-hand side of the arrow, and they go to products, which are on the right-hand side of the arrow. And the reactants are basically what we start with in a chemical reaction. And the products are basically what are formed as a result of a chemical reaction. So these guys are formed as a result of a chemical reaction. So when we take something like Na plus Cl2 and it goes to NaCl, go 2 there and a 2 there. These are reactants, and this is our product. So as we sort of talked about when we're talking about chemical changes, a chemical equation oftentimes represents a chemical reaction, which is a chemical change. You could also have a chemical equation that represents a physical change as well, but a lot of times they do represent a chemical change that occurs. But it's always reactants to products, and on the left-hand side is what we start with, and on the right-hand side is basically what we form, which are known, again, as products. So we're going to talk about energy in this chapter. We're going to talk about some different types of energy and what's going on and some different ways to sort of look at energy. So let's take a look at that here. When we talk about energy, a lot of times what we're talking about, for example, is sometimes referred to, especially when we get to the idea of, you probably have heard of before, the conservation of energy. So energy cannot be created nor destroyed. That is sometimes referred to as the first law of thermodynamics. And a lot of times when we talk about energy, what we're talking about is basically energy transferring from one place to the next. And in chemistry, we think of it as sort of a perfect energy. And the idea is if somebody loses a certain amount of energy, somebody else needs to gain that amount of energy, right? So it just doesn't disappear. So two things we oftentimes look at, especially with thermodynamics or transfer of energy, is the system and the surroundings. And the system is basically anything that you're interested in. So if you're doing a experiment in a beaker, the beaker is your system. If you're doing like an experiment in a test tube, the test tube's your system. Whatever you're kind of doing the reaction or experiment on is usually your system. Everything else is the surrounding. So we have this system kind of what you're interested in. And then everything sort of outside of that is the surroundings. And a lot of times, especially with energy, we look at perhaps the flow of energy from the system to the surroundings. We could also look at maybe the flow of energy from the surroundings to the system. It can flow in both directions. And we're going to talk about a couple of things about energy that we talked about previously. We're going to talk again about exothermic sort of processes and endothermic processes, which I think we touched upon when we were talking about different phases of or change of phases going from solid liquid to gas and backwards. Now, when we talk about systems, there's three types of systems that we oftentimes deal with. There's the open system, and in the open system, you could take out mass. You could also, or exchange mass. You could also exchange energy with the surroundings. So if you think about like an open system, like if you just had a beaker sitting on the desk, it's open on top, so you can put stuff in, you can take stuff out, right? There could be a transfer. It also can give off energy and absorb energy. A closed system typically will prevent the exchange of mass, but you still have sort of the exchange of energy. So if you take like a flask and you put like a stopper in it, right? You now can't have any mass leaving it, right? It's all stoppered and can't escape the top of it. But you could still have a transfer of energy. You could still grab the flask and it may be hot or it may be cold depending on the situation. So you still have that transfer of energy. And then we have an isolated system where we have no transfer of mass or energy. It's really isolated from the outside sort of factors or conditions. So here in an open system, mass could go in and out, heat could transfer. We kind of stopper the top, prevents anything from leaving or entering. So we still have the heat transfer. And again, in an isolated container, nothing's going out, right? Everything's sort of in a very isolated sort of system. Now, when we talk about energy, energy is the capacity to do work or produce change. And energy is sort of the work that can be done, force times distance. There's different types of energy that we do come across. There's chemical energy, and these are energy that's stored within the units of chemical substances. So, for example, if we make bonds or break bonds, which is essentially the only thing that happens when you have a chemical reaction occurring. So if you have a chemical reaction as you go from reactants to products, really the only thing that's happening is on the reactant side, the starting side of the arrow, everybody there is just going to break their bonds. And then on the product side, they're going to reform new bonds, which can create new things, new compounds. And that's coming together on the product side. And that all involves, as we talked about and we'll talk about more, that only involves electrons bonds. So bond making and bond breaking only involves electrons. And that's also why, as we'll talk about in a later chapter, again, we don't make any new elements along the way because we're not changing protons or anything like that. It's only about the electrons. So for example, if we have a bond and we want to break a bond, for example, if we have a bond together like so, we actually need to put energy in there to do that. So energy has to come in, and when it does, they get so much energy, they wiggle apart from each other and they break. And we actually have to put energy in to do so. And as we talked about earlier, when we do energy in or absorbed, that's an endothermic process. Now, if you want to kind of make a bond from two things, you want to make a bond, that is actually a situation where energy is released. So if you think about it, you got two things moving around really fast, they have a lot of energy. As they release their energy, they now kind of slow down, and then they can kind of come together and make the bond in that situation. And that obviously, when we release energy, as we talked about earlier, and we'll talk about more in this chapter, is an exothermic process. So even just the process of breaking bonds, making bonds, has to do with energy and can be exothermic and endothermic. And actually, one way that you can look at a reaction overall is to calculate the energy change that occurs from all the breaking of bonds and all the making of bonds. And the difference between that will tell you, for example, whether or not that overall process is going to be perhaps endothermic absorbing energy or exothermic releasing energy. So that's one way you can kind of sort of figure that out. Potential energy is the energy stored due to an object's position. The classic example of potential energy, right, is, you got the big giant boulder on the edge. Hopefully nobody underneath the boulder on the bottom. And obviously energy can be transformed. So the other classic one, right, is the boulder goes over the edge. When the boulder goes over the edge, you get some kinetic energy, which is the energy that matter possesses due to motion. By the way, when it hits, it is going to transfer energy to the ground. Hopefully, again, nobody standing underneath it, or transfer it to that person. And that brings us to the idea, as I was mentioning before, really the sort of first law of thermodynamics, which is the law of conservation of energy. Energy cannot be created nor destroyed. It can't be transformed from one force to the next. And as I really mentioned earlier, in chemistry, we really do think about it in terms of energy sort of transferring a lot of situations as just like it's just a perfect, sort of transfer of energy. It's going to kind of transfer in a lot of cases from one object to the next as you go through it. Now, when we talk about thermodynamics, thermodynamics is really the study of the interconversion of heat and other kinds of energy. When you take Chem 1B, you'll talk about other things about thermodynamics. You'll learn about the second law and the third law of thermodynamics, which will have to do with entropy, the second law of thermodynamics, which is the craziness and disorder that happens. But one of the things here that we come across a lot in chemistry are things that are sometimes referred to as state functions. And when we talk about state functions, what that means is, for the most part, a simple explanation is this: it doesn't matter how you get there, it doesn't matter the journey you take. The only important thing is basically two things: where you started and where you ended. And that's the idea of sort of state functions. As demonstrated here, energy, pressure, volume, temperature, these are all state functions. If you look at the little picture here, we have two hikers. One took a more direct route up the mountain, and one took the more scenic route around the mountain. But when we look at the potential energy difference between both hikers in this case, they both basically started at the same spot and ended at the same spot. And we would find their potential energy by taking the difference between where they started, where they ended, and where they started. And they have the same potential energy. That is why when we calculate things like you see to the right there, delta E, the change in internal energy, is the final energy minus the initial. It doesn't really matter the process in between. Change in pressure, final minus initial. Change in volume, final minus initial. Change in temperature, final minus initial. A lot of things that we'll talk about here in this class, and you'll learn in future chemistry classes as well, is when we talk about a chemical reaction, for example, and we see a chemical reaction written, like we were just talking about there, like say a reactant going to our products. So a lot of times people, when they see a reaction written, will kind of assume that maybe it just occurs in like one step. It just goes like, hey, reactants directly to products. And in a lot of cases, there are a lot of reactions that actually occur in like multiple in little reactions along the way, that when you add them all together, gives you the overall reaction. So it happens in these little steps along the way. Some could be like 2, 3, 4 different individual reactions that are added together to give you this overall reaction. You'll love that in Chem 1A. That is known as Hess's law, which, can get a little crazy as you're adding up a bunch of little reactions to make a big reaction. But the important thing is where you start and where you ended with. That is why, as we'll talk about here in this chapter a little bit, one of the most common ways that we represent energy in a chemical reaction is what is known as delta H, and we're going to talk more about it in just a second. But delta H is known as the change in enthalpy. And the one way that we calculate it is we take all the energy of our products and we subtract it from all the energy of our reactants. So it's the idea of products is our final state and reactants are our initial state. So a lot of thermodynamic sort of properties, and more you'll learn about in 1B and so forth, are calculated by doing that, taking the thermodynamic property of your products minus the thermodynamic property of your reactants. And that gives you the overall situation that is occurring in this case. Any questions on that there? Why don't we take a break? Yeah, stretch. Okay, we're going to continue on. So we were talking about energy here. Let's go on here. Let's talk a little bit about then some important energy units that we do come across a lot here in chemistry, and obviously some of which you do need to kind of know. The SI unit for energy is a Newton meter, which we don't use too much in chemistry. Meter is a kilogram meter squared second squared. I will say that probably the most common sort of energy units of chemistry are joules, or kilojoules are very common sort of units that we definitely do see. A relationship that does pop up a lot in chemistry, maybe not a lot necessarily in our class, but as you go to Chem 1A, Chem 1B, the relationship between a joule is equal to a kilogram meter squared second squared. So that relationship definitely pop up a number of places throughout chemistry as you go through some different classes as well. So that's probably a good relationship to make sure that you know. The relationship between joules and kilojoules, as we see here in 1 kilojoule, that is 1,000 joules. That's just our basic kilo sort of conversion. Make sure, obviously, you know that as well, because definitely you want, especially when we talk about energy, very commonly energy units are oftentimes given in kilojoules. Sometimes you do calculate in joules, and has to convert to kilojoules or backwards as well. Now, traditionally, chemists do express energy in a form of what are known as calories, and this is sort of like a lowercase c, small c, calorie. And the definition of a calorie is the amount of energy or heat that's required to raise the temperature of 1 gram of water by 1 degree Celsius. I say lowercase c because there is another unit that we will see here that is a capital calorie with a capital C, and that's more of a nutritional calorie. And one of the sort of capitals calories is equal to 1,000 of the little c calories, and that's equal to 1 kilocalorie. Now, units that are also very common with energy, I will say that probably don't come across a heck of a lot in chemistry, but calories and kilocalories are also used a lot. So calories and kilocalories. And it's the same relationship. There's 1,000 calories is 1 kilocalorie. So it's probably something too to just keep in mind. This relationship for sure you should know. And that is the conversion between calories and joules. So 1 calorie, 4.184 joules. As we will see later on in this chapter, that's also known as this, that number will pop up, and that's the specific heat capacity of liquid water. So you'll see that kind of 4.184 number a lot, as that's the specific heat capacity of liquid water. One way that we use energy is to change the temperature of a substance. If we have ice to liquid water, that is a process where we put energy in. When things sort of gain energy and sort of an endothermic process, we typically will see the temperature increase for that substance, right? So it's gained a lot more energy, a lot more movement happening. The result of that is we see a higher temperature. Vice versa, somebody kind of releases energy, like in an exothermic process, we typically will see their temperature kind of go down. Temperature is sort of a measure of what's happening in energy. Again, if you kind of see temperature rising, that means that that substance usually is gaining some energy. Just think of obviously a simple example like with boiled water, I think yesterday, right? Obviously, you put energy into the water, right? The result that temperature goes up. And obviously, if you had your thermometer there as it was cooling down, right, it was releasing energy to the surroundings. And obviously, you see the temperature come down. Now, thermal energy is another sort of form of energy, and thermal energy is really the energy that is related to the random motion of atoms and molecules. And really, the more sort of atoms and molecules you have, the more molecular motion you got going on there. And the hotter the sample would be in terms of thermal energy. Now, thermal energy and temperature are not necessarily the exact same thing. Again, as I mentioned before, a lot of times we use temperature to measure sort of like the flow of energy of what's happening. But thermal energy really has more to do with how much molecules, atoms there are, how much those guys are going to sort of vibrate and give off energy. So just to sort of give an example of that, if you had a cup of coffee here at 70 degrees Celsius and you had like a big old bathtub there, terribly drawn here, at 40 degrees Celsius, it looks just like a bathtub. What we see here in terms of thermal energy is the bathtub would actually contain more thermal energy because obviously in a bathtub you have a lot more water molecules, right? So a lot more water molecules, a lot more motion happening, even though its temperature is less than the smaller cup of coffee. In the coffee, obviously you have a lot less water molecules moving, a lot less thermal energy. The coffee cup has a higher temperature because there is a lot less water molecules. So you will see a greater temperature change if you heated that because there's not as many water molecules to do so. Something that we'll learn about in a little bit later on in this chapter is specific heat capacity. And something like water is 4.184, has a pretty high specific heat capacity, which means if you have a lot of water molecules, it's going to take a lot of energy just to see a 1 degree temperature difference. If you have less water molecules, you're going to take a little bit less energy to kind of see that 1 degree temperature difference. You're going to be able to heat it a lot quicker. Just like if you just think about a water example, right? If you had a big giant pot of water, right, and you wanted to heat it up to um, boil some pasta or something like that, it takes a lot longer, right, to get the temperature up there, right, than if you started with just like a little thing of water, right, and you heated that, that's going to start to boil a lot quicker, right, because there's just a lot less molecules present. Now, heat can be defined as the flow of energy between two objects that are a different temperature. When we talk about the flow of energy or heat, heat always flows from hot to cold, right? So heat is always flowing from hot to cold, and you should think about it that way and remember it that way because it'll help you maybe visualize sort of what's going on. Um, that is why, for example, as I might have mentioned, when you take an ice cube out, right, you don't necessarily have to do anything to the ice cube and it will start to melt, right? Because when you take the ice cube out, it is colder than the room temperature. So all the heat from the room is going to go into your ice cube and it's going to start that melting process. That's also why when you make ice cubes, you take a tray of water and you put it into the freezer. The water is now warmer than the freezer temperature, right? So the heat's going to go out of the liquid water into the surrounding area of the freezer. The result of that is your water of ice or water will become ice at that point and it will basically make your ice cubes. So this sort of process where we talk about the flow of energy is really important in chemistry. And as we mentioned before a couple of times at this point, we'll officially kind of talk about it now. Exothermic processes, again, are any process where heat and energy is released to the surroundings, for example, like striking a match. If you strike a match, or even your Bunsen burner in my demonstration yesterday, right? If you put your hand near it, it is warm coming off of there, right? You could feel the heat coming out and transferring from the fire to the surroundings, and that's case. The Bunsen burner in that case would be your system, right? The surrounding air would be your surroundings, right? As it's happening there, a combustion reaction that's going on. Endothermic processes, again, are all processes where energy is absorbed. And again, it can be the system absorbing energy, it can be the surroundings absorbing the energy, but somebody's absorbing the energy. And typically, when we have a transfer of energy, there is one thing that is exothermic for them, and then the other thing is endothermic. So somebody's going to release that energy, which is going to be exothermic for them. Somebody else will pick up that energy, which will be endothermic for them as well. Now, as we will continue to talk here, ways that we represent exothermic and endothermic, say in calculations or numbers, is also really important. The sign, whether you have a positive number or a negative number for energy, is also really important as to whether or not it's an exothermic or an endothermic process. So as I mentioned a second ago, a very common way that we look at energy is delta H, which is known as the change in enthalpy, and also Q, which is basically the heat or energy associated with something. Heat. Now, when you have an exothermic process, both the delta H and the Q values tend to be negative. So if you were to calculate these things and you end up with a negative value for energy, that typically will end up as a negative sort of value. So if you see, which is a very common thing that is done in chemistry, is you'll have a chemical equation written, and at the end of the chemical equation, they'll go, the delta H for this reaction is negative 200 kilojoules. The negative is really important in that sense because it tells you that process is exothermic overall. If you had one where it said the delta H was positive, it will tell you that it is an endothermic process. So for endothermic process, it is the opposite. Typically, the delta H and the Q values will end up being a positive number when you calculate it. So that's also a pretty good clue as to, again, whether you're dealing with overall a endothermic or exothermic. And really the number in this situation for both delta H and Q is not all that important. It's actually the sign that's really important. Now, I say that because it's something to really keep in mind as you're doing calculations. And sometimes people are taught, especially early on in chemistry, like, don't worry about the sign, just, do the calculation. But really the sign is really important, especially when you're calculating something about energy. And whether or not you end up with a negative value or a positive value will tell you a lot about what's going on in that reaction. So if you have to do a calculation, and this very commonly occurs in the temperature aspect of a calculation, a lot of times you always want to kind of do the temperature calculation correctly, especially when you're calculating, as we will see, something for specific heat. You always want to kind of do final temperature minus initial temperature. And if that does give you a negative sign, that's actually quite important in terms of the overall energy of what's going on. So let's take a look here at these two diagrams. And these two diagrams are what are sometimes referred to as energy diagrams. And we have an exothermic energy diagram and an endothermic energy diagram. And as I mentioned before, in a chemical reaction, reactants going to our products. And basically what's going to happen on this side is we're going to break all these bonds. And again, on this side, we're going to make all these bonds. And as we talked about earlier on in this chapter, again, both of those processes do involve endothermic processes and exothermic processes as to what you're doing. So when we look at an energy diagram here on the left, this is exothermic. This right here is our reactants. So this is where, in terms of energy, our reactants are starting. And down here is basically where our products are ending in terms of energy. Now, one of the easiest ways to identify that this is a exothermic reaction is when I look at the energy of my reactants where I'm starting, and I look at the energy of my products where I'm ending, my products are in lower energy than my reactants. And the only way for my reactants to get down in terms of energy is you have to get rid of some of that energy, right? So if you lose some energy, you're going to drop overall in terms of energy. And energy has to be given off in this case. So whenever the energy of your reactants are higher than the energy of your products, energy is released. And that's going to be an exothermic process that's going on in this case. And that's different than if we look at the diagram on the right. The diagram on the right is an endothermic process. And when we look at the guy on the right, our reactants are down here. So this is where our reactants are starting. And this is where our final products are ending in terms of energy. And when we look at the difference between where our reactants started and our products ended in energy, our products are actually higher in energy than our reactants. So the only way for the reactants to get up there in energy is you got to toss some energy in for them to go up to a higher ending state. And that is an endothermic process. So the energy of our reactants in this case are less than the energy of our products. And that is an endothermic situation that's occurring here. Now, some of the other things that we see here as we go from reactants to products is what is happening in this reaction as this occurs is we are breaking those bonds on the reactant side and we're making some new bonds. Now, in order for a reaction to actually occur, there's two things that has to happen. Things got to collide with each other, and they actually have to collide with each other with the right amount of energy. So just because two reactant molecules like bang into each other, it does not guarantee that you're actually going to make some product. They actually have to hit each other in the right spot, kind of like the active site. They got to actually hit each other in the right location. And they have to hit each other with the right amount of energy. That minimum amount of energy that's required for a reaction to take place is what is known as the activation energy. And the activation energy is the minimum amount of energy required for a reaction to take place. And activation energy is sometimes abbreviated E of A. So if you see E of A, that is talking about the activation energy. When we actually look at the diagram here, the activation energy is actually this hill right here. So if you come right here, all the way to the top of the hill, that is the activation energy right there. So that is your activation energy. And if you look at your endothermic one, it is down here where the reactant started, all the way up to the top here is your activation energy hill in this case. Now, the activation energy hill, what's happening as they are climbing this hill. So as we kind of go, kind of clear out some of this here. Actually, no, I'll just redraw it here. So as we look at an energy diagram such as this, our reactants to our products, energy, and our E of A. What's happening as these reactions start to climb this hill and get to the very top here is we have the bonds starting to break. So all those starting stuff is starting to break their bonds. We actually have at the same time the formation of new bonds. So sort of like, okay, we're going to start to separate and we're going to also start to make some new bonds at the same time as they climb the hill. And when they get to the very top of the hill, this is probably the highest point in energy. This highest point in energy is what is referred to as a transition state. And what you actually have at the very top of this hill is a transition state complex. It's actually a species that has partially made bonds and partially broken bonds. So you got this guy that's like, okay, I'm not fully broken and I'm not fully made yet, kind of right there in the limbo stage. And that is why it is the highest point in energy. Because one thing that you should know about chemistry in general is, much like us, being in high energy is not a good thing, right? So things want to always be in the lowest state of energy that's possible. And a lot of things that happen in chemistry is all for like trying to lower the overall energy that's happening. So a lot of times when reactions take place, bonds take place, it's all about sort of dropping the overall energy. So in this process, as you climb to the very top of this activation energy hill, you have this species where got partially made bonds, partially broken bonds, not a super stable situation. It very quickly will kind of drop down to the other side and go to the other side and make your products. That's why in a lot of reactions, people oftentimes will have a very hard time trying to isolate that little guy at the top of the hill because it's super unstable. It doesn't hang around a very long time in most cases, and it will kind of go to the other spot. Now, if we look at sort of our, and this is our exothermic, we look at our endothermic one, which looks, let me draw that right there. Looks to me something like this. Endo. Again, our activation energy is right here. And it also has the same thing. We could see that when we compare the hill that the reactants has to climb in the exothermic reaction to our endothermic reaction, we can see that the endothermic reaction has a much larger hill to climb, right? And that is why in an endothermic reaction, overall energy is absorbed, right? A little extra help to get up and over that hill, right, to the other side. That activation energy hill plays a really important role in how fast or slow that reaction takes place. If that hill is relatively small, you're going to have a lot of reactant molecules that's not going to have a problem to get up and over to the other side. Probably will occur really fast. If you have a really big hill that everybody's got to climb to get to the other side, most likely that reaction is going to occur a little bit slower than that, much like in life, right? If you had a small little speed bump in the parking lot, you can get up and over no problem. You got to climb the giant mountain to get to the other side. You know, not too many people are going to go climb the mountain, right, to get to the other side. It can take you much longer to get to the other side. So that activation energy is really the energy barrier for reactant molecules to get to the other side. And that's also why not all collisions will result in products being formed, because when they hit each other, you might just not have enough energy to climb that hill to get to the other side, and has to wait for somebody that does have enough energy basically to get to the other side. Any questions on that? Now, how do we talk about delta H? And we talked about delta H being either negative here and delta H being positive in an endothermic process. The way that we calculate delta H very commonly, and we'll do like a couple of examples of it, but to calculate the delta H, we basically take the delta H of our products minus the delta H of our reactants. And again, remember, we're talking about state functions, right? So we're talking about like final state, initial state. So again, products are final state, reactants are initial state. Now, if we just look at the diagram, in order to calculate the delta H from this reaction here, we would take the energy of our reactants, we would take the energy of our products. The difference here is actually the delta H of this reaction. So if I were to calculate it here without numbers, I would take the delta H of my products, which is a small number in terms of energy because it's way over here, minus my reactants, which is a higher number or a larger number. And when you take a small number minus a larger number, you end up with a negative value when you actually calculate it. If you look on the endothermic side, our delta H is the difference between a reactant our products. And once again, if we were to calculate it here, our products are higher in energy, so it's going to be a larger number, minus our reactants, which are smaller in energy. And a large number minus a small number will yield you a positive number in this case. So that is why when we say, if you see a delta H that's negative, it will imply that this is going to be an exothermic reaction. And if you have a delta H that's positive, it'll be an endothermic reaction. Any questions on that? Now, since we have the diagrams here, actually, we'll do it here, maybe, yeah. There is one way that we can, if we needed to, for example, if we needed to speed up a chemical reaction. And typically, if we need to speed up a chemical reaction, we add what are known as a catalyst. And a catalyst sometimes are added to reactions. And really, for the most part, the purpose of the catalyst is to speed up the reaction. And that's really the purpose of it. A catalyst is not a reactant. It is not a product. And it does not get used up in the reaction. It is there simply to facilitate that reaction happening more efficiently and faster. If you look at a chemical equation, a lot of times the catalyst is written on top of the arrow. So a lot of times you'll see the catalyst written on top of the arrow. For example, it could be something like platinum. It could be something like an acid, H plus, as a catalyst. So sometimes you'll see things written on top of the arrow, and in a lot of cases, those are the catalysts. So what does a catalyst really do? So as I mentioned before, what a catalyst does is essentially it finds a more efficient way for that reaction to take place. So for example, it could be a solid catalyst. And for example, let's just say we had some gas molecules that are flying around, and these are reactant molecules, right? So we got some gas molecules kind of flying around, and gas molecule A, gas molecule B. And if they were just flying around by themselves, we would have to wait, frankly, for them to, kind of find each other, right? They got to fly around and kind of find each other. And that could take a long time in some cases. I mean, not always, but it could take a longer time. Now, if we added, for example, a catalyst, like a solid catalyst to this, like a well-drawn square, and in this solid catalyst, maybe both of these gas molecules are going to be attracted to the catalyst. And what that will do now is put those gas molecules basically in the same location, and they're not going to have to go hunting with each other, right? Just randomly flying around and hope for it to happen. They will now be in a very good location. And sometimes they can even help with the breaking of bonds and making of bonds as well. And that just puts them in a more efficient way of them coming together rather than just hopefully, two are going to collide in the right situation. And it just kind of brings everybody in a nice place. It's kind of like the old cartoon, right? The Roadrunner and the Coyote, right? The Roadrunner finds the trapdoor through the mountain, goes straight through the other side, right? And you have to go up and over. So it's kind of like you've got a big hill to get to the other side. You find like a little trap door that takes you straight across rather than going up and over the big hill to the other side. Now, what does that do in terms of our energy diagram? When you have a catalyst, because it finds a really more efficient pathway for this reaction to take place, it actually is able to lower the activation energy. So the activation energy in the catalyzed reaction versus in the uncatalyzed is much smaller. And what that does is, because it's much smaller, it allows a greater proportion of molecules to go, cool, I don't need all that energy to go up and over the big hill, but I do have enough energy to get over the smaller hill. And because it has enough energy now to get over that smaller hill, That's going to allow more reactive molecules to get to the other side. The end result of that is the rate of that reaction, how fast it happens, will actually happen a lot quicker because everybody looks at the hill and go, "Oh, I could probably get over there. I got enough energy to do that," rather than the big hill and they go, I'll just stay on this side. Never mind. I don't really want to go. So by lowering that sort of energy barrier, it results a lot of times with a catalyst in the reaction occurring faster. And that's typically what a catalyst is usually used for, to speed up a chemical reaction. There are actually negative catalysts that are used sometimes to slow down reactions, but I would say most of the time, 99% of the time, if you're having a casual conversation about catalysts, why you're doing that, by the way, I don't know. But if you're having a casual conversation about a catalyst, most of the time, most people are talking about it's kind of speeding up the reaction. But there actually are ones that are known as negative catalysts that will kind of slow down a reaction as opposed to a positive catalyst. Any question on catalysts there? Here's just some different forms of energy diagrams, but again, what we see here is the characteristics we talked about. These are our reactants, and this is our products. So again, reactants higher in energy than products, energy being given off in this case as a result of that. Down here, this is our reactants, that is our products. And once again, energy's got to go in for those guys to get up there in terms of energy. So to summarize some of our exothermic, endothermic talk we've been having, again, exothermic released. I don't know how often you would actually see it written like this, but it can occur. When we think about an exothermic reaction, we think of energy as being a product. And sometimes, not too often really in our chemistry classes here, but sometimes you may actually see an energy value actually written into the equation on the right-hand side or the product side of the arrow. And that would indicate that this is a exothermic reaction. So if you actually see a energy value written on the product side, it is indicating that that reaction is exothermic. As opposed to here, where you see an energy value sort of written on the reactant side, like it's being gained or absorbed, that's going to tell you it's an endothermic. I would say in most cases, you would see this reaction written with a delta H at the end and a negative number for it. And that's, again, the most common way in chemistry that you kind of see exothermic or endothermic. They just simply give you that delta H value, and whether or not it's positive or negative will tell you that. And the same thing down here, you most likely would probably not necessarily see it written in there, but you might have a delta H value given to you that is positive. And again, that would indicate that is endothermic. Obviously here, that flow of energy in an insulated container, we've got 90 degrees on the left, 10 degrees on the right. So in this case, heat and energy flowing from hot to cold. So our guy on the left there is going to kind of cool down. Our guy on the right is going to gain some of that energy, can cause those molecules to start moving faster. Guy on the left is going to lose that energy, going to start to slow down a little bit in terms of molecular motion. As you can see, it will probably meet at the end somewhere in between the two temperatures. So 90 and then 10 is 100 divided by 2. Both of these guys might eventually come to equilibrium at about 50 degrees on both sides of the container as that energy is being transferred from one side to the next. In this case, on the left-hand side, the process is sort of exothermic, right? It's releasing its energy. On the right-hand side, that all those water molecules are gaining the energy. It's endothermic, and they're picking it up. So let's talk a little bit about enthalpy. And you'll see it again more in 1A, but we'll talk a little bit about it in here. Enthalpy, like I said, or the change in enthalpy, is the most common way that we do see energy related in sort of chemistry and chemical reactions. And you could think about the change in enthalpy, which is delta H, as basically the energy sort of difference in a reaction, whether or not overall that reaction is going to release energy, or overall is that reaction going to gain energy. Now, the way we calculate it, like I said before, is it's really like a state function. So we take all the delta H values for the products and we subtract it from all the delta H values from the reactants. And that's going to yield us either a positive or negative value. Now, if you're given just the chemical equation and nothing else, just the chemical equation, and you're like asked, what is the delta H for this reaction? Where do you get the numbers from? The good news is you typically would get the numbers from a table. So you would go to a table and look up the values. And usually in the table, they're sometimes referred to as the delta H of formation or delta H of F. These are table values. And you would look it up for the substance you're looking for. And you usually want to be really careful. Not that we're going to look too much of these tables up in this class, but when you get to 1A and 1B as well, you always want to, when you look at these tables, which typically can be found in the back of your book, you usually will find what are known as a thermodynamic value table with delta H, delta S, and delta G values in there. You want to make sure whatever you're looking for is what you're looking for, and it's also in the correct state. Is it a gas? Is it, a solid? Is it aqueous? You want to make sure you find it in the correct state. The major one, and people always screw up on when they kind of go to those tables, is water, because usually you'll find water in the liquid state, the solid state, and obviously the gas state as well. And they just pick like the first water they find in the table without realizing it's maybe a different value because it's in a different state. So let's just say, for example, how do we calculate this? If we had a made up sort of reaction like 2A plus B goes to 3C, and we would go to, say, a table of delta H, and let's just say we got A, B, and C. We'll go A is minus 40 kilojoules. We'll go with B as 125 kilojoules. And we'll go with like maybe C is, I don't know, we'll go, how about 75? We'll see how we do. Kilojoules. All right, so remember again, on the left-hand side of the arrow, these are our reactants. And on the right-hand side of the arrow, these are our products in this case. Now, we're going to assume the balanced equation in this case. And we want to calculate the delta H for this reaction. So to do this, we are going to take our products minus our reactants. But there is a couple of things that we do have to kind of take into account when we do have a reaction like this. Do you have a question? Or no? Oh, no. Okay. So when we look at the coefficients here in the balanced equation, that's a 1, again, not usually written, and that's a 3. We actually do have to take those values into account when we do this calculation. Now, those values are what are sometimes referred to, as we'll talk about in a later chapter, moles. And really, those values that I wrote in that table are probably kilojoules per mole. So we actually multiply the coefficient by the value we see in the table. So we're going to start on our product side. So the delta H for this reaction, we're going to take our products, which in this case is 3Cs. We do need to take the 3 for the coefficient, and we need to multiply it by the value that we find in the table for C, which I made up at 75 kilojoules. And basically, that's going to take care of all of our products. If I had more than one product, I would do the same thing for the next one and add them together. I'm now going to subtract the difference from the reactants. So on the reactant side, I have A that has a coefficient of 2. So I'm going to take 2 times the value of A from the table, minus 40 kilojoules. I'm then going to add it to my other reactant, which is B. And again, the coefficient there is 1. So I'm going to take 1 times my value of B from the table of 125. And that's going to be our reactants. So again, we're taking products minus reactants, final state minus our initial state basically here. Let's see how I did in my made up numbers. So we're going to go 3 times 75 minus 2 times negative 40 plus 125 basically. Let's go here. And it looks like maybe we end up with 180. kilojoules in this case. And that would be our delta H for this reaction. First off, any question on the calculation there? By the way, based on my calculation, would I say this reaction is endothermic or exothermic? It is endothermic. My delta H value here is a positive value. So here we ended up with a positive value. So that is going to be endothermic. Question on that. And obviously, if you ended up with a negative value at this point, overall that reaction is going to release energy. Overall, this made-up reaction here is going to need to absorb some energy as a result. Any questions on that? All right, let's try one or two here with some real numbers. All right, so for this reaction, what is the delta H of it? And is it endothermic or exothermic? And these would be the values, obviously, you would find from the table. So this reaction here, calculate the delta H, and is it exo or endothermic? Take a few moments, and then we'll talk about it. Okay, so let's take a look. So once again, if you're just given an equation, obviously these numbers would be provided for you. But if you find it somewhere else, you may have to go look it up in a table in the back of your book, these numbers. And again, we're going to do our products minus our reactants. So our delta H here is going to be the delta H of all of our products added together minus, the delta H of our reactants. So we're going to start on our product side, which is on the right-hand side of the arrow. So that's going to be, again, taking the coefficient into account, 2 times the value of NaOH, which is minus 470 kilojoules, plus the coefficient here, which is a 1, times the value of H2, which as you can see is 0. And that basically takes care of all of our products in this reaction. We're now going to subtract it from all of our reactants here. And in this case here, we're going to go to our reactant side. We have 2 of the sodiums, and that's going to be 2 times the value of sodium, which is 0, plus 2 times the value of water, which is minus 286 kilojoules. And that's going to be all of our reactants. Right? So again, products minus reactants in this case. So popping that into a calculator, 2 times minus 470 minus basically 2 times minus 286. Looks like a winner maybe. Too many extras, parentheses. Gonna get us a minus 368 kilojoules, looks like. Yeah. Any question on the calculation? Endothermic or exothermic, this one? This one is a exothermic reaction. Again, we have a negative, so exothermic. Yeah. Again, as I mentioned, in terms of just determining exothermic or endothermic, number is not all that important. It's actually the sign that's important here, positive or negative to determine it. Any questions on that one? Let's take a look maybe at another one here. All right, so let's give this one a go. See what you come up with. Same thing, calculate the delta H. Those are the values, I believe. Okay, so let's take a look at again. We're going to calculate it the same way. We're going to do our products minus our reactants. So again, we just want to add up all of our products from the table and add up all of our reactants. Basically, subtract them. So we'll start here with our product side. So over here, we do have 16 of the COs. We're going to take 16 times the value of CO from the table. We're going to then add it to our next product, which is 18 waters, minus 286 kilojoules. That again basically takes care of all of our products. We're then going to subtract it from our reactants, again doing the same thing. We got 2 here, so that's going to be 2 times our value in the table, minus 208. And again, we do have 25 oxygens. Good news is they are all 0 from the table there. And by the way, for delta H values from the table, anything in a standard state that's really uncombined, you will see a value of 0. So that's a common one for things that are just by themselves. So 16 times -110 plus 18 times -286. Gonna get us something like maybe a minus 6908 on this side, minus our other side there, which is 2 times -208, minus a minus 416. So it looks like here that minus that. Gonna get us a negative, looks like 6492 kilojoules. Again, we have a negative, so once again, we are looking at a exothermic reaction in this case. Any questions on how to calculate delta H? Again, I would say probably the most common way in chemistry that you kind of can look at an equation or an equation is given to you and sort of that energy component given to you as well as that delta H value. I will skip that one, I think. The next thing we're going to talk about is a very common sort of energy value and way that we calculate energy or heat, and that is specific heat, or more specifically, specific heat capacity. And specific heat capacity has a definition very similar to calories. The specific heat capacity is the amount of energy needed to raise 1 gram of a substance by 1 degree Celsius. And there is a specific heat equation, which apparently the box jumped out of the way, which is down here. But basically, Q is equal to ms delta T. This is our specific heat equation, which is this one here. Obviously, you do need to know it as well. Let's talk a little bit about what each of these sort of values are. Q is basically the heat or energy. And the typical units that you have for Q is joules or little calories. So those are the two typical units associated with Q. I would say in our class, we tend to use joules more than calories, but calories is sometimes used, but most of the time it's probably going to be joules. M in this case is the mass, and that is in units of grams. S in this case is the specific heat capacity, and it has units of either joules per gram per degree Celsius or calories per gram per degree Celsius. It actually has 3 units associated with it. Those 3 units are basically in units, what the words say as the definition. The amount of energy, joules, required to raise 1 gram of a substance by 1 degree Celsius. So that's why it has those 3 units. It is essentially the definition. Very, very commonly, people screw up by mixing up the Q and the specific heat capacity. So Q should only have 1 unit, either joules or calories. The specific heat capacity should have 3 units, joules per gram per degree Celsius or calories per gram per degree Celsius. I personally use S for specific heat capacity. A lot of books do, but instead of S, some people will use C for specific heat capacity. Some books and some people will use SH for specific heat capacity. So you'll sometimes see instead of the S there in that formula, either C or SH used depending on the book or the person. I personally will use S most of the time, but again, C and SH is a common sort of other units or sort of ways that they're used. Now, T here is our change in temperature. Our delta T is our change in temperature. And that is exactly calculated. You want to take the final temperature minus the initial temperature. One of the few things in chemistry in terms of temperature, it's in degrees Celsius. So one of the few things that is not Kelvin, probably the only time you'll have a temperature that you want to leave in degrees Celsius here. So probably 99.9% of the time you want to convert to Kelvin like we talked about, but this is one of the few. The reason for that is here in chemistry, our specific heat capacities are usually given in degrees Celsius. If you take physics or something like that, they sometimes roll with Kelvin over there, but here we do kind of roll with the degrees Celsius in our specific heat capacities, and that's why we want to make sure we do that. Now, one number that you definitely should know is the specific heat capacity of water. And by the way, this is liquid water. Bless you. And the specific heat capacity of liquid water is that number that we saw earlier, 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. That is essentially the conversion factor we saw earlier, that 1 calorie is 4.184 joules. So this is basically the same number, same conversion, but the specific heat capacity of liquid water is that, and that is, again, something they expect you to know. So make sure that you do know that. I say liquid water here because, as we will see, if you have ice or steam, which is obviously water, just in different phases, the specific heat capacity for ice and steam are about 2 joules per gram per degree Celsius. So it does change if the phases are different. But that's one you should definitely put in the memory bank. You definitely use it a lot along the way. Now, just like delta H, when we calculate Q, and we end up with a negative number, it is going to tell us this is an exothermic process. We're going to release energy. And if we calculate Q, we end up with a positive number. It's going to be an endothermic process. So this is really important in this equation. Probably one of the most important things in this equation, as it may not seem all that important, but it actually is this part of it. It is the delta T and the change in temperature, and making sure that you do final minus initial. And that is because when you look at the other values here, mass is always going to be a positive number. Specific heat capacity is always going to be a positive number. So the only thing that will turn your Q into a negative number versus a positive number is that change in temperature part. So you do not want to just take the difference of the number. You want to always do final minus initial, because if it is a exothermic process, your final temperature will be less than your initial, and that's going to give you the negative value that you need for your Q. If it is an endothermic process, your final temperature will be larger than your initial temperature, and that will give you the positive number that you should end up with. So it is really important for, as I mentioned, that change in temperature part, to do always the final temperature minus the initial temperature, and that will always take care of, do I have the correct sign or not the correct sign? It will take care of it for you when you do that. Any questions on that? By the way, you can simply do this, and we will do it in a later experiment, to figure out things like energy and heat release by using just a very simple, what's known as a coffee cup calorimeter. Stack a few coffee cups together, a lid. You use a thermometer to figure out the change in the temperature of water, and you can calculate how much heat or energy basically was released. When you do that under constant pressure, which most cases you are in the lab, you're actually calculating the delta H of the reaction, the enthalpy of the reaction. So you can actually calculate the enthalpy of a reaction by simply just using coffee cups and a thermometer, basically. So you don't need anything super fancy. In a lot of cases, to do that, you could actually do that with just very basic equipment. Here is a table similar to the one you have in your book of the specific heat capacity. As I mentioned before, they do want you to know this number, and obviously the 1 calorie per gram per degree Celsius version as well. As you can see here, ice is 2.03 and water is 2, so it does change with different things. And you can see there are things like aluminum, iron has some different specific heat capacity. When you have a large specific heat capacity, that means it takes a lot of energy to move the temperature of 1 gram of that substance by 1 degree Celsius. If you have a small specific heat capacity, Doesn't take as much energy, right, to change the temperature of 1 gram of that substance by 1 degree Celsius. That's why something like water has a very high specific heat capacity. That is also very much why people get a little nervous when like the ocean temperature changes by just a very small degree, right? If you think about how much water is out there and how much energy is needed just to move the tick just that little bit, it's a lot of energy, right? So, um, again, that's also why, for example, when we had the coffee cup, it had just a little bit of water in it, right? Versus the bathtub, we can see a much bigger temperature difference quicker because we don't have as much mass involved in the situation. All right, let's try one here. Determine the amount of energy as heat required to raise the temperature of 10 grams of aluminum that has a specific heat capacity of 0.89 joules per gram per degree Celsius from 25 to 58 degrees. Give your answer both in joules and calories. So take a few moments here and see what you come up with. Okay, so let's take a look. So obviously we're doing something with specific heat, so that hopefully should pop the equation up for you, ms delta T. And again, usually a lot of good things to do in a problem is just to take out the information and label it. We want to determine the heat, so we're looking for Q. Obviously 10 grams is a mass. We have the specific heat capacity given to us, 0.89 joules per gram per degree Celsius. And it's going from 25 degrees, which is an initial temperature, to a final temperature of 58 degrees. So basically, we got everything that we need there on the right-hand side. So we can just plug and kind of chug it into this guy here. So Q in this case is going to be our mass, which is 10 grams, times our specific heat capacity, 0.89 joules per gram per degree Celsius, times, again, we want to go final temperature minus initial temperature. So 58 degrees Celsius minus 25 degrees Celsius. In terms of units, again, we're multiplying here. So grams and grams will cancel. Degrees Celsius will cancel. And obviously that's going to leave us just joules left over as our unit in this case. And it looks like if you punch that into your calculator, you got a 293.7 joules. We do want to look at some sig figs because they do say it is a chemistry class here, so we probably should. So obviously here we got 3 significant figures. Here we got 2. And really here we're subtracting, so we are going to decimal places. They both do not have a decimal place. So when we do that subtraction, we get 33 technically degrees Celsius, which is also 2 significant figures, which means sig fig wise, we really should go to 2 significant figures here since we're multiplying and we want the least number of sig figs. So sig fig wise, that's like a 290, no decimal, right? So we don't have 3 significant figures in this case. First off, any question on that part of the calculation? It also wants us to convert it to calories. So we want to use our conversion between joules and calories. And again, 1 calorie is 4.184 joules. So we'll take our proper sig fig number there and we'll go with 4.184 joules on the bottom, 1 calorie on top, again, multiplying the top, dividing the bottom. The joules are going to cancel. We'll use the rounded number, I guess. There we go. We'll end up with 69 calories in this case. If you did not round, you would end up with 70 calories, right? If you kind of use the whole number. I would probably either. As long as it ended up at 2 sig figs at the end. Any questions on that? But if you did 70, right, you would need a decimal point there at the end. Yeah. Show that one. Yeah. I did because in this case, the rounded number was also an answer that we wanted to give, so I used it. I would have took either one, like I said. Personally, I probably would have if I was not just teaching it like I was there, I probably would have took the 293.7 and divided it. And like I said, you're good for me on either one if you ended up with 70 versus 69. But in this case, since we did have to round to give an answer for the previous step, I just took the rounded number as that was an answer for the question. All right, let's try another one here. We got 294 joules of heat is transferred to 10-gram sample of silver at 25 degrees Celsius. What will be the final temperature of the silver? Specific heat capacity here of silver is 0.24. Okay, so let's take a look again. Obviously, we're doing specific heat, so pop up our equation. We have 294 joules. That again has 1 unit. So I do know that is Q. So remember, Q has 1 unit and the S has 3 units associated with it. We got 10 grams, which is a mass. At 25 degrees Celsius, which is an initial temperature. And we're looking for a final temperature in this case. And we have a specific heat capacity, which again has the 3 units associated with it. So we have everything we need here to actually solve for delta T. So we have basically all these things. So if we want to solve for delta T in this case, we're going to take these guys here and divide it to the other side. And that will give us delta T is equal to Q divided by MS when we divide those guys to the other side. Popping in our numbers here. We got 294 joules up on top. We have a mass of 10 grams. And we got our specific heat capacity here of 0.24 joules per gram per degree Celsius. In terms of units, joules on top and bottom cancel, grams cancel. We're left with degrees Celsius. When we divide, goes to the top, degrees Celsius. So we pop all that into our calculator here, and 294 divided by 10 and divided by 0.24. I pop that in there, right? And I'm going to end up now on my calculator with a 122.5 degrees Celsius. Now, a couple of things about this number. That is not the answer, right? Because that is just the change in temperature. That is not like the final temperature. I am not going to round in this case because that is not an answer I'm going to give, right? So I'm going to continue on with the calculation. But I do want to be careful of where I should actually stop, right? Technically speaking, on the next step. So if we want to kind of look at sig figs at this point in the calculation, we are looking at dividing and multiplying. So really, this guy's got 3, this guy's got 3, and this guy's got 2. Technically, if I were to round this number at this point, I should actually end up with something like 120. Again, I'm not going to really round at this point because, again, it's not an answer I need to give. And I want to probably be as close to really the right answer as I can. And if I round 120 versus 122.5, that's a pretty good difference in numbers. Right? So I'm going to lose a lot of sort of accuracy there as I'm rounding. So I'm just going to keep that in mind where that number should be, and that will help at the end. So delta T here, which is the change in temperature, should be our final temperature minus our initial. And we are looking for our final temperature here, which means we're going to add that to the other side. And that will give us that our final temperature is our change in temperature plus our initial temperature in this case. And we're going to go, and like I said, I'm going to keep track of where I should be, which is here. And I'm going to add it now to my initial temperature, which was, what is that, 25, looks like. And now I'm going to take the whole number there plus 25, and that's going to give me 147.5 degrees Celsius. At this point, I could really clean it up. And technically speaking, number would have been a 120, which is a whole number, right? And I basically added it to a whole number, which really means in this last part here, I should end up with a whole number. And at this point, We would round up, and 148 degrees Celsius would be the right sort of answer in this case. Question on that there. So again, in this case, versus the last one, again, in the last one, I rounded because that number was a number I want to give as an answer, right? So I want to make sure it's the sort of the correct number sig figs. But here, I'm going to really avoid rounding to the end and kind of keep track of everything. Any questions on that? All right. So let's talk a little about heat transferred from one object to the next. And as I talked about, we do think about sort of energy and heat being transferred sort of perfectly. So whatever amount of heat and energy somebody releases, somebody else is going to pick up that energy. So the overall transfer of heat, if you took like water and you put a piece of metal in it, should end up being zero. So if we take a look at this situation, let's say that we had a beaker of water here. And let's just say we had, I don't know, we'll go with 110 grams of water. And we'll say the initial temperature of my water was, we'll go 27 degrees Celsius. And we have a piece of metal over here. So we got a metal in this case. And let's just say we have 69 grams of this metal. And let's say we heated this metal up to like 99 degrees Celsius. So we took this piece of metal, we heated it up to 99 degrees Celsius. We got like a little beaker of water over there at 27 degrees Celsius. And I decide I want to toss my piece of metal into the beaker. And as a result of that, the temperature of the water in the beaker will maybe rise to, we'll do 30.5 degrees Celsius. Right. So first off, when I put that hot piece of metal into this water, which way is the heat flowing in this case? Is it flowing from the water to the metal or the metal to the water? It is metal to water. The reason it's flowing from the metal to the water is because the metal is hotter, right? So again, heat and energy is going to flow from hot to cold. So when you toss that piece of metal into this beaker of water, it is going to release all its heat and energy to the water. So in terms of the metal, it is exothermic, right? It's releasing its energy. In terms of the water, it is endothermic. It's picking up all that heat and energy. If I toss that piece of metal into water and just leave it there, eventually what temperature will it come to? It should come to equilibrium with the water's temperature, right? So if the water temperature stopped at 30.5, that piece of metal is now sitting in 30.5 water. It's going to also be the exact same temperature. So in this process, when you do this, the metal at the end, actually know the temperature of the metal in the water because it should be the exact same temperature as the water's final temperature. So the final temperature of our metal in this case would be 30.5 degrees Celsius. It is going to be the same because it's basically sitting in the same water, basically. Point. Now, let's say in this case, we wanted to try to figure out what is the specific heat capacity of the metal. Now, we could use basically the water in this case to allow us to figure out the specific heat capacity of this piece of metal. And that is because the one thing we know about liquid water always is the specific heat capacity. And the specific heat capacity of liquid water is that 4.184 number that you will come to love. And if we take a peek over here on our water side, and we take a peek at our specific heat equation, we have the mass of the water, we have the specific heat capacity of the water, we have the final and initial temperature of the water. So we have all the information that we need in this case, figure out how much energy the water will gain when we toss that hot piece of metal into it. So let's do that for the water. We're going to now figure out, based in this example, for the water, how much energy is going to gain. So the mass is 110 grams. Our specific heat capacity, 4.184 joules per gram per degree Celsius. Again, final temperature, 30.5 minus initial, 27 degrees Celsius. That's going to get us here. Going to get us here 1610.84 grams will cancel, degrees Celsius will cancel, joules. That is how much energy our water picked up from the result of you tossing a hot piece of metal in there. Is that many joules. I obviously haven't sig-figged it at this point, so I'm just going to kind of leave it at that number for the time being, and we'll come back to it in just a second. Now, how does that help us when we think about the metal? If we take the specific heat capacity or specific heat equation for the metal, Q of the metal will equal ms delta T. We know we have the mass of the metal given to us. We have our final and initial temperature of the metal. And we are looking for the specific heat capacity. So the one thing that we are actually missing in order to calculate the specific heat capacity of the metal is actually the amount of heat or energy the metal lost in this case. And we could do that because we know how much energy the water gained. What should be in this case the only source of energy that the water gained? It all came from what thing? It all came from the piece of metal. So all the energy that was lost by the piece of metal is all the energy that we just calculated was gained by the water. And we could use that relationship of Q of the metal will equal negative Q of the water. So our Q of the metal will be negative 1610.84 joules because it should have lost the exact amount of energy that the water gained. Why is the negative important here? Because for the metal, it is exothermic, right? And for the water, it's endothermic, which is why we ended up with a positive value for Q. And for the metal here, we end up with a negative value because it's exothermic and releasing that energy. First off, any questions on that? So this is a very common practice that you could basically, because you know the specific heat capacity of liquid water, like I was saying earlier, you could take a coffee cup, some water, and a thermometer, and you could figure out how much energy the water gains. And all that energy gained by the water would be all the energy that was lost in this example by the metal. By the way, you could also do it the opposite way. The water could actually release the energy, and whatever you put in the water, it could actually gain the energy. So it can go either way. And it doesn't always have to go in this direction. So how does that help us with our calculation? Well, I now know my Q of the metal by using water's relationship there. And now I could solve for S. So I'm going to take both of these guys and divide it to the other side. And that will give me that the specific heat of the metal will equal Q of the metal divided by m delta T. I'm going to put my numbers in. My Q is going to be negative 1610.84 joules. My mass of my metal is going to be 69 grams. And now probably a really important part at this point is the change in temperature. We need to go final minus initial for the metal. So the final temperature of the metal is 30.5, yeah, not 90, right? That's initial. So if we want to go 30.5 minus 99 degrees Celsius. That's important because when I do the subtraction, what type of number am I going to get? Positive or negative? I'm going to end up with a negative value That would be really helpful because now I have a negative there. And those two negative values is going to turn my specific heat capacity back into a positive value, which is what it should be. So that's again an important thing to always do final minus initial so you don't end up with some wonky like negative specific heat capacity. So you want to make sure you do that. All right, so if we do that there, we're going to go divided by 69 and divided by our 30.5. Whoops, probably helps hit the right numbers. 30.5 minus 99. And not too bad by making up numbers. Going to end up with 0.3408. I'm going to take it to a few digits here for a second. And by the way, none of these units cancel. They all stay there. So this is going to be joules per gram per degree Celsius. Again, none of the units cancel. First off, any questions on the calculation? Change the temperature of water, how much energy is either gained or lost by water. You can water and figure out things about that. Let's talk about sig figs here. So if we go back to our original calculation, we had 4 sig figs, we had 4 sig figs, and when we subtract that, I believe we ended up with 2 sig figs, which means technically speaking, we should be out here, over here, at about 1600 when we do that first calculation. And that means technically when we come over here, we now would have 2 significant figures. This guy would be 3 significant figures. And when we subtract down here our 99 and our 30.5, we end up with 3 significant figures. So because of the very first calculation, really our answer should end up at 2 significant figures, which means we should end up at 0.34 joules per gram per degree Celsius as our specific heat capacity for this metal. Any questions on that there? So the sort of common way to figure out things like heat capacity. And again, you can even do real reactions, where you add acid bases together because a lot of solutions are water-based. So you can use the specific heat capacity a lot to figure out the change in enthalpy. Any question on that there? All right, we're going to lay it up there for